In this video, we're going to be discussing section 5.5 out of the OpenStax Calculus book, Volume 1. This section deals with one of the most important things that you will learn in the entire Calculus 1 course, which is U-substitution integration. U-substitution is the method that we use to undo the chain rule. In other words, we have some integrand that was derived by using the chain rule for derivatives, and we need to unravel it and undo the derivative. This is one of your bread and butter techniques that you will use from now on in all math classes from here on out, except possibly linear algebra. What we do is we set the part of the integrand to be u, and then we look for the differential du. Remember that if the variable, independent variable, is x, then the differential du is stripped of what would be in the denominator position dx, where the dx is swung around to the opposite side of the equation. Then we can make a substitution for the differential dx so that we can switch it to the differential du, as well as substituting in whatever we decided u should be. This will result in a change of variable from whatever the original variable was, usually x, to the variable u. Knowing what to pick for u is the key to doing u substitution well, and you cannot proceed in calculus unless you can do u substitution well. It will be on almost every single exam, if not every exam you take from here on out. Here's the theorem from your textbook, which covers u substitution with indefinite integrals. They allow u to be some function g of x, where the derivative of g is continuous over an interval. Then they define another function f to be continuous over the range of g that corresponds to the same interval over which the derivative of g is continuous. Remember that the range represents the y values of a function. That's because we're going to compose f and g and put g inside of f. Thus, it doesn't matter that f would be continuous on a different interval. We need f to be continuous over the y range of the inside function g. We'll let uppercase letter f of x be an antiderivative of lowercase letter f. Then we can state that the integral of the composed function g inside of f times the derivative of g will give us the integral of the outside function f with the substitution u equal to g of x inside of it with respect to the derivative of u instead of the original differential dx. This will give us the antiderivative function, uppercase letter f of u, which is, of course, g of x, plus some unknown constant. Now let's prove this, since you probably have no idea what this means yet. We'll go through the proof and then we'll work some examples. Most students do not really get an understanding of what U-substitution is until they've been practicing it and doing examples for at least a day. Don't be surprised if U-substitution takes a while to click. It will click, and it must click in order for you to move on in calculus. Here's the proof of U-substitution to undo the chain rule for derivatives. Again, suppose we have two functions that we'll use lowercase letters f and g to represent. Suppose that lowercase letter g's derivative is continuous over some interval named capital letter I, and that the function f is continuous on the range or y values of the function g, so that you could compose f with g. Suppose that we also know what one of the antiderivative functions for lowercase letter f is, and that we call this uppercase letter f. Now we're going to compute the derivative of the antiderivative with g on the inside. In other words, the composition of the antiderivative with the function g inside of it. Now, at first, there's no reason for students to understand why on earth we do this. You'll see how it works out at the end. But again, this is one of those proofs where someone started at the end and backed their way into it. We are, in a sense, starting at the end and trying to back our way into figuring out how to unravel the chain rule for derivatives. If we do the derivative of uppercase letter F with G inside of it, the composition, then by the chain rule for derivatives, we would get the derivative of the antiderivative, freezing the inside function, which is represented by g of x, times the derivative of the inside function, which is, of course, g prime of x. This is just basic chain rule. So far, so good. However, since uppercase letter f of x is one of the antiderivatives of lowercase letter f, then we know that the derivative of the antiderivative must be the original function. In other words, if you take the derivative of an antiderivative, you've gone in a complete circle and ended up back where you started, which is the original function, lowercase letter f of x. We're going to take this relationship that you see here at the end of the first line and plug it into this relation here you see at the top. We rewrite what was at the top, taking the derivative of the composition of the antiderivative function, uppercase letter f, with g of x plugged inside. This will give us derivative of the outside times the inside alone, or with the inside plugged in, times derivative of the inside. Basic chain rule. Now we know that the derivative of the antiderivative is f, so we can replace that with the original lowercase letter function f composed with g times g prime of x. Now, we're still backing our way into the problem. We've started at the end, well, partway through, and we're going to back our way to the beginning. Now we're going to choose u to be the function on the inside, the one that we're putting on the inside when we do composition. We can apply the derivative to this function g, which, since it is equal to u, also gives us du dx. Now we abuse the notation by stripping the differential dx away from the notation du dx and swing it to the other side of the equation. This lets us write that the differential du is g prime of x times dx. This is one of the most important steps here and is crucial for doing u substitution correctly. Now we're finally just about ready to put it into the integral. Over that interval over which the derivative g prime of x is continuous, this means that if I have the integral that you see here, which is the derivative of the antiderivative composed with g, that if I have that, then I can rewrite this as f of u du, since g prime of x dx is equal to the differential du, and I can substitute it in, and g of x is equal to u, and I can substitute that in place of g of x. However, now that I have rewritten the indefinite integral in terms of another variable u, and I know that uppercase letter f is an antiderivative for lowercase letter f, then I can say that this indefinite integral must be the antiderivative evaluated at u plus some unknown constant. I can then back substitute and take the u out and replace it with g of x. And this gives me finally the antiderivative composed with g of x plus some constant. That's the end of the proof. I have yet to see a student be able to easily apply u substitution from just the proof. We need to do some examples. In this case, a lot of examples. This is such an important method that I have split this section into 2 videos. In the first video, we will be taking a look at basic u substitution for both the indefinite and the definite integral. In the second video, I'm going to take a look at what I call tricky U substitutions. These are U substitutions that are not obvious and for which you need to be shown the trick at least once so that it might occur to you in the future that you could do it again. Let's take a look at the first example. In this first example here, what we want to learn how to do is pick the right U. Sometimes there is more than one possible choice for U, and sometimes there is only one choice for U that will make the integral work. You have to know where to look for U, and you have to be able to find it relatively quickly to be able to solve equations in the amount of time you're given on a typical Calculus 2, Calculus 3, or differential equation exam. If you're going to be an engineer, U substitution is going to be there every step of the way. If you're looking at these, to pick the right U, you want to think about the order of operations, just as you did when you did the chain rule for derivatives. These are, in a sense, composed functions. We have an outside and an inside. That inside function is a good choice for U, but again, it's not always that obvious, and sometimes that's not actually the best choice for U. Sometimes it is the right choice, but unfortunately, you have 2 or 3 choices for what is, quote, the inside function. So which one do you pick? Here are some good locations to look for the inside function to pick for U equal g of x. First off, the denominator of a fraction. I would say that given a choice between the denominator and numerator, I typically choose the denominator. I'm not going to say this always works, but that's where my gut leads me 9 times out of 10. For example, when we're looking at this indefinite integral here, the choice for U that you should take is x squared plus 5 is equal to U. Another good place to find U is underneath the radical symbol itself. The expression under a radical is called the radicand. Whatever is underneath it, whether it's a square root, a cube root, a fifth root, or a 42nd root, that is a good place to find U. In this case, in this problem, there are expressions outside the radical and under the radical. What is under the radical, known as the radicand, is the correct choice of U. Another good place to find U when you have an exponential function is the power on the exponential function. You must be sure that you know the difference between an exponential function and a power function. In an exponential function, the base is a constant like e or 5 or 2. In a power function, which we have here, the base is the variable or an expression involving the variable, but the power itself is a constant. Make sure you know the difference because where you look for U depends on which kind of function you have. If you have an exponential where the base is a constant and the variable's in the power, then that power with the variable in it is a good choice for U. In this problem, x squared plus 5. In this one, where it's a power function, I have conflicting things. I have here a simple x being raised to a second power, which might make x a decent choice of U, but I also have in parentheses x cubed minus 75, and that whole binomial is raised to the 5th power. In this case, I would look for the more complicated thing, and its inside is x cubed minus 75. That makes it the more likely choice for U. Note I said likely. You need to be comfortable with getting it wrong sometimes. This is normal. This is what mathematicians do. We're wrong a lot, but we've learned not to let it bother us because what we've learned are techniques to find what works if we don't give up. So if the first choice of U you pick doesn't work, back up and pick something else. What about this one in between those two? This is a trig function. In a sense, trig functions and logarithms or natural logs have similar places to find u. The best place to find u, if all you have is a natural log or a trig function, is in the argument to that trig function or natural log function. Looking at this problem here, 3 theta is the argument inside of sine, and that makes it the best choice of u. Now I've put it in parentheses, but be aware that that is not required, and that sometimes those parentheses will be left off. You have to know that the 3 theta is the argument for sine, and that it is the right choice for u. Similarly, when we look down here at natural log, we have inside the natural log the expression 3x plus 22. The argument to natural log is the appropriate choice of u here. Let's now work each of these examples and show how to do the u substitution integration. Here are the steps that your book recommends for solving an integral by u substitution. It says to look at the integrand and select an expression for g of x. That's u. Find the u. Once you've found u, you need to compute the differential du. Once you've found du and u, you need to substitute them into the integral. This step typically involves some algebra and arithmetic, especially on substituting in the differential for du. Now that you've rewritten the integral with respect to u instead of the original one, you should be able to integrate it. Be aware that there are problems where you have to do u substitution more than one time. In other words, you make one substitution and it ends up giving you something else where you need to do another u substitution. In that case, don't use u for the next time you do it. I wouldn't use v either because it looks too much like u. I recommend omega, which looks like a lowercase letter w. Once you've completed the integral in terms of u, you're not done until you get the answer back in terms of the original variable, which is usually x, and whatever g of x or u was. In other words, first you get out of the original variable and substitute to u, and then you've got to back your way back out and get out of u and back to the original variable. This was the first example we had up above when we were trying to find the right place to find u. In this example, because this is a rational function, the best place to find u is probably the denominator. And again, I have to say probably because this is not a hard and fast rule. In this case, I get u equals x squared plus 5. Now let's compute the derivative of u with respect to x. I'll start off slow, working out every single step, and then I'll start showing you how we really do it. And as you know, we usually skip a step here or there. The derivative of u would be 2x, the derivative of 5 being 0. Now we abuse this notation for du dx, and we swing the differential dx to the opposite side so that we can isolate the differential du. We're trying to get the dx that's in the original integral out and replace it with du. This lets me then write du equals 2x dx. Now I'm going to substitute. This is where it gets its name. It's sometimes called substitution and also u substitution. In this case, I'm going to replace the x squared plus 5 with u. I also need to replace the x and the dx. At this point, you have a choice. There's more than one way to proceed. In fact, I can think of at least 3 good ways. I'll show you a couple of them. Here are the first 2 ways I recommend. The first way is method 1, solve for dx. If you solve for dx, then you're taking the expression that you have for the differential du and you're isolating the dx since that is exactly what you have in the original that you're trying to get rid of. This would give me dx equals du divided by 2x. Now, what would I do for my next step? For my next step, I would replace, and so far I've only replaced the x squared plus 5 with u. Now I would replace the differential dx with what it is equal to, which is du divided by 2x. Don't forget that you also have this monomial factor x in the numerator. It's not gone, it's still there. Once I get to here, though, I can simplify. X in the numerator and x in the denominator, those are going to cancel. That would lead to the following indefinite integral. 1 over 2u times the differential du. Now, the 1/2 is a constant, which, as you know, can be brought outside the integral since it does not depend on the differential, which is now du. This would give me 1/2 the integral of 1 over u du, or du over u. The antiderivative to 1 over u is the natural log of the absolute value of u. This leads to 1/2 the natural log absolute value of u plus a constant. I'm not done. This variable is not the variable that appears in the original problem. That variable was x, which related to the differential dx. I have to get back there. So I back substitute and replace the u with x squared plus 5. That gives me my final answer of 1/2 the natural log of the absolute value of x squared plus 5 plus a constant. In this case, x squared plus 5 can't possibly be not positive, so you could replace the absolute values with parentheses, but you cannot drop them entirely because all of this expression is inside the argument to natural log. You could also write it in a slightly different way. Once you recognize that this part is in fact strictly positive, you can also take the 1/2 at the front and pull it inside as a power on the argument. The 1/2 power is the square root, so you could in fact write the natural log of the square root of x squared plus 5 plus a constant. That's method 1. In method 1, the difference is we solve for the differential dx and we substitute just that in place of the differential. Let's look at method 2. In method 2, we do it a little bit differently. I will say that my preferred method is probably a hybrid of the two, but more like method 2. In method 2, what I do is I look at the problem and I go, okay, my differential du is here. It is 2x times the differential dx. What of this part of du is already present inside of the integrand that is not being replaced with u? Since x squared plus 5 is replaced with u, it's gone. But what's left behind is the x dx. That will be this part here. In other words, I have x dx already. I just don't have the 2. So what I do instead is I solve for what's present other than u. That means that I need to isolate x dx since that's what's still left in the integrand to replace. That would give me that du divided by 2 is equal to x dx. That will now let me rewrite the integral as 1 over u du over 2. Notice that this cuts out the step where I have to cancel the x's because they're already gone. I did that step as a part of isolating what was left behind. Since the 1/2 is a constant that does not depend on the differential u, I can bring it outside and I again get du over u, which is from here on out exactly like the blue side, and I would get exactly the same answer. Let's look at another one. This is the second example that we saw up above. In this particular one, we have a radical inside the integrand, but we also have a binomial factor, which is not a part of the radical. When given these two choices, probably the best place to pick u first, or at least to try, is the radicand, the thing that is under the radical, whether it's a square root, cube root, or whatever. If my u is x squared plus 4x minus 5, then what would du be? In order to find du, I first find du dx by taking the derivative of both sides of that equation. That gives me 2x plus 4. Now, I abuse the notation and split the differential dx away from the differential du and slide it to the other side. It will be multiplied by what's on the other side, so now the 2x plus 4 must go in parentheses. Now, I look at what's here and I look at what's up here in my integral. We'll do both methods again. In method 1, we did solve for the differential dx. Let's try method 1 again. In method 1, we were to isolate dx. If I isolate dx, that means I need to divide by the binomial 2x plus 4. That gives me that dx is equal to du divided by 2x plus 4. Continuing on down, the next step would be to substitute into the integral and replace u for the radicand. This would give me the integral of x plus 2, which has not been replaced, is not a part of du that we see, and is not a part of the radical or u. You'll see in a minute it is actually a part of du, it's just hiding. Now for the next part, I replace the radicand with u to get the square root of u. The differential dx is replaced with du divided by 2x plus 4, the binomial factor. The next step is to do something to simplify the expressions that still have the variable x in them, the original variable, so that they go away. I cannot integrate until I have only one variable, and the variable needs to be u, so x has to go. That means I've got to do something to 2x plus 4 so it looks like x plus 2. Hopefully you've already noticed that it does have a common factor of 2, and in fact, it has an x plus 2 factor as well. That will allow you to cancel out the x plus 2 binomial factors and will leave behind the constant factor 1 divided by 2. Now we can rewrite this in the next step. In rewriting, I can pull the 1/2 outside the integral, and this will give me the square root of u du. Now I need to write the square root of u in its power form, which is 1/2 u to the 1/2 power du. And then I can do the power rule for integrals by adding 1 to get 3/2, dividing by 3/2 or multiplying by 2/3, and adding on the constant of integration. The 2's will cancel, and this gives me 1/3 u to the 3/2 plus c. This is not the final answer until I'm back to the original variable, which is x. U in this case was x squared plus 4x minus 5. That gives me 1/3 times x squared plus 4x minus 5 in parentheses, all raised to the 3/2 power plus the constant of integration. Let's look now at method 2, which is sort of a hybrid, and cuts off some of these steps by manipulating the differential du to reveal the parts of the integrand that were not a part of u to begin with. When I look at the original and I let u be the radicand, then I know that I'm going to be able to rewrite this as the integral of the square root of u. That leaves behind the x plus 2 binomial factor and the differential dx. Now you look at the differential du and you see if you can find an x plus 2 binomial factor already present in the differential du. And in fact, I can. I can write du as 2 times x plus 2 dx. That means that the x plus 2 dx is already present in the integral. All I need to do is solve for x plus 2 dx, since it's already there, by dividing both sides by 2. This leads to du over 2 to replace the x plus 2 times the differential dx. This is our substitution factor. When I rewrite the integral now, what I end up with is the integral, the x plus 2 dx is all replaced with du over 2, and the radical is replaced with the square root of u. Again, this cuts off a few steps and allows me to pull the 1/2 to the front, and again, think of it as the square root of u du. From this point, it is identical to method 1. Let's look at another example. In example 3, we have a product of 2 different types of functions. We have x as a monomial factor, which is of course just a linear polynomial. We also have an exponential function, e, which is being composed with a third function, which is a quadratic polynomial, x squared plus 5. When given the choice between the two, go for the more complicated part. Find the inside function. What is done here is an x squared plus 5 has been placed inside the e. In other words, if you were to evaluate it, you'd first have to square the x, then add the 5, then you would put it into the e. Since the last thing you did was put it into the e, the thing you put in is the inside function u. That makes u be x squared plus 5. If we're going to work this one out, the x on the outside, the monomial factor, at first does not appear to be a part of u. Let's see if it becomes a part of du. When we look at this and we take the derivative of u, we take it with respect to x. This will give us 2x. Then we abuse the notation by separating the two differentials and swinging the dx to the other side, so we can isolate the differential du. We're trying to switch from the differential dx to the differential du inside the integral. This is why we need to isolate du. For the next step, it depends on which method you want to use. If we use method 1 again, then we would again solve for dx. Some students prefer to do it this way forever. Some students start this way and switch to method 2. Some students move back and forth depending on their mood and the difficulty of the problem. It doesn't matter. Whichever one works, they're both equivalent and correct. Now, if we solve for dx, I would have to divide both sides by 2x, so that the differential dx is the differential du divided by 2x. Putting this into the integral, the monomial x is still present. It is not a part of dx, and it is not a part of u. Then I replace x squared plus 5 with u in the exponential function factor. I replace the differential dx with what I found here in method 1. That is du divided by 2x. For method 1, you have the extra step of needing to cancel out the x's. Once we have the x's here, we can cancel those out. that should lead to the following. This would give us then, and 1/2, which is a constant factor, which we can pull outside since it does not depend on u. This leaves e to the u du behind. Now, e to the u is the easiest integral to evaluate. It is both its own derivative and its own antiderivative. We love exponentials. This gives me 1/2 e to the u plus a constant. Rewriting it then in terms of x requires to back substitute that u is x squared plus 5. That means I get 1/2 e to the x squared plus 5 power plus a constant. Some students, when handwriting, will put parentheses around the power so that it's clear that it is a power and it doesn't somehow creep down to the line where it's not supposed to be. Let's take a look at method 2. If we're looking at method 2, we are looking at the integral. We know we had the monomial factor x. We know that the power on the exponential will become u, and we need to know about the differential. Those are the parts where the question mark are. How much of that is in the differential for du and how much is not? If I look now at the differential du, the question marks represent an x and a dx, an x and a dx, which is this part here. So in method 2, I would solve for what's present and in the differential du, which is x dx, by dividing both sides by 2. That gives me that x dx can be substituted out for du over 2. This lets me write the integral as e to the u times du over 2. This, of course, also leads to 1/2 e to the u du. From this point, it's identical to method 1. Let's take a look at another example. I'll be honest with you, I picked a lot because there is no way you can do too many examples of u substitution. The more you do, the better off you will be. In this particular example, we have a trig function sine. The argument to the trig function is not simply the variable by itself. It is instead 3 times theta. That makes the argument to the trig function 3 theta the best choice for u. From now on, we're simply going to use the hybrid method 2 to solve our problems. However, if you prefer method 1, solving for the differential, feel free to go ahead. I will mark out what dx is, or d theta in this case. Let's take a look. If we're looking at this problem and du is 3 theta, then I would need to find du d theta, not dx. Since the original variable is theta, I have to take the derivative with respect to the differential that appears in the original integral here. That's what has to be in the derivative when you apply it to u. That gives me just 3. When I abuse the notation then, I get 3 d theta, which is a pretty easy differential for du. Now, when I want to substitute that out and I look up here, I can see that I can replace the argument to the trig function with u. That only leaves me d theta. That's the only thing that's still present in the integrand and not accounted for. That's that part there. That means I need to solve for the d theta in this one. In fact, method 2 and method 1 are identical here. D theta becomes du divided by 3. I replace it up here with du divided by 3. The 3 is a constant factor in the denominator, which can be pulled out of the integral since it does not depend on the differential now, which is u. This gives me 1/3 the integral of sine of u du. Now remember, we're looking for the antiderivative of sine, not the derivative. Yes, the derivative of sine is cosine. But what do you have to take the derivative of to end up with positive sign? That would be negative cosine. So this gives me a 1/3 times the negative with the cosine of u plus a constant. Don't stop here. Many students make the mistake of assuming that once they've integrated, they're done. You're not done until you're back to the original variable, which is theta. We need to replace u with 3 theta. This gives me minus 1/3 cosine of 3 theta plus the integration constant c. Let's move on to another example. In this example, which is a little bit more complicated in some ways, we have two polynomial expressions multiplied together, x squared as a monomial factor and x cubed minus 75 as a binomial factor. The x cubed minus 75 is also being raised to the 5th power. In that sense, this part is more complicated. That makes it the better place to find u. Well, then what is u? Well, if I were to imagine plugging in an actual value for x, let's say 1 to make it easy. 1 cubed is 1. 1 minus 75 is negative 74, and then I raised it to the 5th power. In other words, the last thing I did was the 5th power. So everything that came before that must be on the inside. That makes x cubed minus 75 the inside function, which is u. This time we're going to do something a little more advanced, and we're going to abuse the notation at the same time we solve for the derivative of u. In other words, instead of writing du dx, I'm going to write du, find the derivative of it, which would be 3x squared, and abuse the notation by swinging the dx around all at the same time. This is what real mathematicians do. We don't like unnecessary steps, but we won't leave out a step that is necessary. So we'll take a shortcut and abuse the notation and swing the differential for the original variable to the other side while we're finding the differential of the new variable u. Now I look at this and I try to identify, well, what is already there inside the integrand, including the differential that is in the differential du. Inside the original integrand that is not a part of u, and remember this part here becomes u, is the dx and the x squared. That would be this part here. That means solving for what's already present, I have x squared dx is equal to du divided by 3. If you want to solve for the differential using method 1, you can do that. In that case, you would have dx equal to du divided by 3x squared. And that is what you would use to replace dx. Using my method for method 2, you would instead replace the x squared and differential dx with du over 3, and you would replace x cubed minus 75 with u, but notice that the 5th power has not been accounted for. It's still there. It's sitting on u. Now, the 3 in the denominator is a constant factor which can be pulled to the front, so I get 1/3 the integral of u to the 5th du. Now I just do the power rule for integrals, and this would give me 1/3 u to the 6th divided by 6 plus the constant of integration. 1/3 times 1/6 will give me 1/18, but I have to get back to the original variable, which was x and not u. That means that I replace u with the binomial factor x cubed minus 75 enclosed in parentheses with the 6th power on it, plus the constant of integration. Take a moment and think about that one and make sure that you understand the steps before proceeding to the next example. For our next example, you will need to remember the special integral that we learned in one of the sections previously. If you have not learned this integral yet, I'll give it to you here. This may be one you're not familiar with, but after you've learned about the derivative, or rather not derivative, but the integral of natural log, come back to this example and see if you can understand it. The integral of the natural log of x with respect to x is given by x times the natural log of x minus x plus a constant. In our example, if we're going to use this formula to find it, and again, this is not something I would expect you to have memorized. In fact, you will learn a better way of doing this when you get into Calculus 2, called integration by parts. I would not expect you to know this one off the top of your head. In this case, to apply the rule, however, we need to find u, which we decided was the argument to natural log, 3x plus 22. In our case, then, we can find du and abuse the notation at the same time by taking the derivative of both sides, which gives us 3, and swinging the differential dx over to the right. This gives us du is simply 3 dx. I don't have 3 dx inside the original integrand. Remember that this part becomes u. The 3 is missing. This is also just like method 1 in that all that's present is the differential, so I need to solve for the differential dx, which was originally present. That gives me du over 3 to substitute in place of dx. This gives me the natural log of u times du over 3. However, I know the over 3 is really a constant factor of 1/3. You're now ready to go ahead and take another shortcut, and instead of writing the du over 3, split the factor and pull the constant part to the front on the outside of the integral. This will also save you a step. Is it necessary? No. Is it easier? No. Does it save writing? Yes. In the next step, what we want to do is apply the formula you see here. Since our variable of integration is u and not x, we'll replace these x's here in the formula with u's. This gives me 1/3 the natural log of u times u on the front minus u plus c. Now, this x is not that x. We need to get out of this u and back to our original u and our original variable x by substituting backwards that u is 3x plus 22. This gives me 1/3 times 3x plus 22 times the natural log of the absolute value of 3x plus 22, which it should be there, minus, I'm running out of room, 3x plus 22 plus a constant. Now, the next thing you could do on this problem is you could distribute the negative to clean that up a little bit. If you wanted to pull the 1/3 in as a cube root, you could do that, but there wouldn't be any point in distributing the 3x plus 22 over the natural log. In fact, on this one, I'd be tempted to leave it exactly the way it is here. This form of it reveals more clearly that these three parts are in fact identical and reveals the form of the equation. I would leave it like this. Next example. Now we're looking at example 7. This is the integral of e to the 3x plus 1. If you have the integral of e to the 3x plus 1 with the differential dx, there's only one place to find u. It has to be in the power on the exponential function, and that is our u. This is the first example where you've not been given the u, but instead you've got to find it yourself. I think that u should be 3x plus 1. I'll find the derivative of u and abuse the notation at the same time to get the differential du is equal to 3 dx. I don't have the 3, so instead I solve for the differential dx by dividing both sides by 3. Now I can substitute in the original integral that it's e to the u and replace the original differential dx with du divided by 3. The du will go to the back of the integral as the bookend for the integral symbol, and the constant 1/3 will move to the front. This gives me 1/3 e to the u plus c, which of course could be rewritten in terms of the original variable x as 1/3 e to the power 3x plus 1 plus a constant. Let's take a look at another example. In example 8, we have a cosine function. There's nothing else present, but it does have an argument that's more complicated than the previous trig problem we did. In this case, the argument is 2x plus 5. That's the only place to find u, so that's got to be u. Let's try it. If u is 2x plus 5, then the differential du is 2 dx by taking the derivative of both sides with respect to x and swinging the differential dx around to the right, called an abuse of notation. Now I don't have the 2 since this center part becomes u, which means I can solve for the differential dx and get du over 2. Substituting into the original integral then, I get cosine of u, replacing the differential dx with du times 1/2, pulling the 1/2 outside. The antiderivative to cosine is sine. This gives me 1/2 sine of u plus c. Now I have to go back to the original, which is u is 2x plus 5, to get my full answer, 1/2 sine of the binomial quantity 2x plus 5 plus the constant of integration. Let's take a look at example 9. Example 9 is quite a bit more complicated. It looks more complicated, and in some ways it is more complicated. This one is sort of an exception to one of the rules I indicated before. One of the rules I indicated before, which isn't really a rule, but more like a guideline, is the denominator is a good place to find u, and it is a good place to find u. But in this example, I have conflicting things going on. I've got a radical, but the only thing that's under it is x. A monomial x does not make a good u. In fact, I can't think of any case where monomial x by itself is ever going to be u. 3x, maybe. X? No. That means that this might not be u. I could use the whole denominator as u. That is a possibility. But in this case, in comparing the numerator and denominator, the numerator is more complicated. It has 2 terms added together, and a radical, and the power 4. That makes it more complicated. The last thing that would be done in the numerator is the 4th power. Inside of the 4th power is the square root of u plus 1. In this case, I would go with the numerator over the denominator, but only because it's being raised to a power and is more complicated. I would let u here be square root of x plus 1. Let's see if I'm right. To compute du, we take the derivative of both sides with respect to x. Remember that the square root, the derivative will be 1 over 2 a square root. And then applying chain rule, the derivative of x is, of course, just 1. Now, the derivative of 1 is 0. Be very careful that you don't accidentally write plus 1, forgetting that you are, in fact, taking the derivative with respect to x. Swing the differential around to the other side. This means, if I clean it up, that I have 1 over 2 square root of x times dx as the differential du. Of that, what is present already inside the integrand that is not a part of u? Remember that this part in here becomes u to the 4th power. Well, looking at it, everything else that's left is in fact exactly du. I need a differential dx, and I need 1 over 2 square root of x, which is what I have. This lets me then substitute for the next step. I'm going to replace u, or rather the square root of x plus 1, with u and raise it to the 4th power. The 1 over 2 square root of x times the differential dx is replaced by du. This becomes a very simple power integral. You just apply the power rule for integrals and make it u to the 5th divided by 5 plus a constant. Now you have to back substitute to get out of u and back to the original variable x. Make sure that you put it in parentheses. You can either leave the 5 in the denominator, or you could pull it to the front as a constant factor of 1/5. Personally, I kind of like the constant factor of 1/5, but it's just a personal preference. That would be your final result. This is a much trickier problem, and again, finding u is an art, not a science. There is intuition in it, but remember that when a mathematician says intuition, what they're really saying is, I have done hundreds and hundreds of these problems, and my subconscious is telling me that it has seen something like this before, and this is what I should try first. That's all intuition is. It's your experience over hundreds of problems telling you which way to try first. Let's take a look at a different one. In example 10, we have 2 trig functions involved. We have sine of theta being raised to the 10th power and cosine of theta as another factor with the differential d theta. When you have one trig function raised to a power, that is typically the one you want to pick to be u. It's more complicated. It's not just cosine theta. It is, in fact, remember that you can write it this way, the sine of theta to the 10th power times the cosine of theta d theta. Can you see that this is more complicated? And writing it in this form, you can clearly see what's on the inside is sine of theta. The better part is thinking ahead, which is what you need to start trying to do. The derivative of sine theta is, cosine theta. And when I abuse the notation, I'll get that d theta. So now I let u be the inside of what's being raised to the 10th power, which is sine of theta. Du gives me cosine theta, and abusing the notation swings the d theta around. That's exactly what I've got. I've got exactly cosine theta d theta. That part gets replaced with the differential du, and I can write the integral of u to the 10th du, which again is just a simple power. This gives me u to the 11th power divided by 11 plus the constant of integration. This would give me 1/11th, or again you can leave it in the denominator, times, now we'll replace u with sine again, sine to the 11th power of theta plus a constant. You can also write this as sine theta in parentheses with the 11th power outside. That's perfectly acceptable. But I will say that most mathematicians will use the first notation instead because we're just too lazy to write those 2 parentheses symbols. Let's look at one more pretty complicated example. This is a function you've probably seen before. This is, in fact, one of the ones we looked at the beginning of the semester. This is tanh, or the hyperbolic tangent function, which is sinh divided by cosh, hyperbolic sine divided by hyperbolic cosine. It is, in fact, an exponential. It simply has some properties and identities that are very, very similar to trig identities, which is where they got the name hyperbolic trig. They are, however, based on hyperbolas, not circles, hence the name hyperbolic trig. Though really, they're not trig at all. They are, in fact, exponentials. Okay, what you think? Where should we go to find u? Is the numerator significantly more complicated than the denominator? No. When I say more complicated, I mean you have a composition of functions that makes it more complicated, or additional factors that makes it more complicated. I have two terms in the numerator that are subtracted and two terms in the denominator that are added. One is not more complicated than the other. In that case, I will almost always choose the denominator to be u. I could be wrong, but that'll be my first try. In this case, then, I'm going to write that u is equal to e to the x plus e to the minus x. Then I compute the differential du. Derivative of e to the x is e to the x. Remember when you take the derivative of e to the negative x that you must apply chain rule, which will pull the negative to the front since the derivative of negative x is negative 1. All of this is two terms, which must go in parentheses, so you can swing the differential around dx to be multiplied by the whole thing, not just one part of it. Now we look at that and we compare it to what's left. Remember that I substituted for the denominator, which leaves the numerator and the differential dx, but that's exactly what I got for du. That means that when I do my substitution for u and what's left, I have exactly du over u, which I know the antiderivative for must be natural log of the absolute value of u, plus the constant of integration. Then I back substitute and I replace it with the natural log of the absolute value of e to the x plus e to the minus x. Let's take a moment to talk about this. A lot of students are tempted to want to try to reduce the natural log with the exponential part because they know that natural log and e to a power are inverse functions. However, natural log is an operation and it does not distribute. You cannot do anything because of the plus. You could, if you wanted, drop the absolute values and enclose it in parentheses, but you cannot drop them completely. There has to be something to indicate that it is the sum of those two terms that's the argument to natural log. There's nothing you can do to simplify this further. I can drop the absolute values because both of these exponential functions are strictly positive, and adding strictly positive values always results in a positive. So I can't possibly get anything not positive under there, and that means I can drop them. Let's now deal with the definite integral. We've done a lot of indefinite integrals since doing the indefinite integral is the basis for starting the definite integral. In other words, if you're going to do a definite integral, you have to first find the antiderivative, which means you have to do the indefinite integral. The end is different because you plug in the values of the limits of integration. But up to that point, it's identical to the indefinite integral. There are two methods for doing a u substitution with a definite integral. I use both methods. I don't have a clear preference for one over the other. I do literally use them both. Sometimes I use one, sometimes I use the other. Sometimes it's just my mood, sometimes it's just what I happen to think of first, and sometimes it's a conscious choice because I think it will be easier in the long run. You need to be able to do both because there will be occasions where one is a clear advantage over the other. So this is one where you need to learn both method 1 and method 2. Let's talk about what they are. In method 1, we're going to switch completely to the variable u, and that means we're also going to change the limits of integration from being x values to being u values. When you switch completely, by switch completely, I mean, unlike the indefinite integral, we will never go back to x, the original variable. We'll stay in u all the way to the end. That is sometimes an easier way to do it. Method 2 is more like the indefinite integral. You switch to the variable u just so that you can evaluate and find the antiderivative function. Then you switch back to the original variable, which is often x, by substituting back for u. You keep the original limits of integration throughout the entire problem, but you need to remember that when the differential in the integral changes to du, you can't just write a and b anymore. If a and b are x values, but the differential switches to du, you are required to write x equal a, x equal b, so that the person looking at it clearly knows that a and b are not u values, but are instead x values. This also protects you from yourself, because many students will, if they don't write it that way, forget that they're not actually u values and just plug them in for u instead of waiting to get back to x before they plug them in. Let's look at some examples of these methods. We'll do both methods on the first few so that you can see how it is done. This is example 12. In example 12, you can tell it's a definite integral because, of course, you have limits of integration, numbers at the bottom and the top of the integral symbol. You are not getting an antiderivative family of functions up to the constant plus c. You are instead getting a finite real number representing the area between the curve and the x-axis between the vertical lines x equals 0 and x equal 2. That's what you're getting. Now when we look at the integrand, you see that you have a rational expression. More than that, in comparing numerator and denominator, denominator is definitely more complicated. I have a quadratic in parentheses being squared. That makes it the best place to find u. Since I have something in parentheses being squared, it's the thing being squared that's probably u. Let's make the substitution and see what we get. If I let u equal x squared plus 1, in method 1, let's remind ourselves, we're switching completely to u, and we are never going back to x. Okay, that means that if I'm going to u, I've got to get rid of these limits of integration because they're x values. I know that because the differential is dx. That means I need to then figure out what they are. First, we'll find du, which is 2x, swing around the differential dx to abuse it, and yes, because I planned it, we got a 2x dx, which is the part that's not going to be replaced by u to the power 2. Now, let's deal with those limits of integration. I usually actually do write it in words because I know when I look at it later, I'll go, why did I write that? But if I write when x equals 0, comma, u equals, then I know that what I was doing was substituting out the limits of integration from x values to u values. Now, how can I do that? Well, easy. I know what u is. It's x squared plus 1. If x is 0, then u has to be 0 squared plus 1, which is 1. What about when x is 2? This would give me 2 squared plus 1, which would give me 5. Now be careful here, Sometimes, even though the x limits of integration increase from the lower to the upper, when you substitute in, replace them with the y values, they decrease. No, you do not get to automatically switch them. What will replace the 0 must be the 1. What replaces the 2 must be the 5. If you don't like the order they're in, you can always switch it, but remember that that pulls a negative outside the integral. In this case, I'm happy enough with them the way they are. This lets me rewrite the original definite integral now only in terms of u. This will take it from, instead of 0, u equal 1, and instead of x equal 2, u equal 5, and I will replace the 2x dx with the differential du, and I will replace the x squared plus 1 quantity squared with u squared. Now that it is in u form and all u form, which includes, of course, the limits of integration, I can rewrite the 1 over u squared in a different power form, which is u to the negative 2 du. Now I can apply the power rule for integrals, and I would get u to the negative 1 over negative 1 evaluated between 1 and 5. Next step, of course, would be to plug in the limits of integration. However, as I pointed out earlier, if you don't like what you have and you want to switch the limits of integration, you can. Remember that what it does at any step, including here, is it throws another negative into the mix. But I already have a negative, so what's a double negative? You got it. A double negative will make it positive, and u to the negative 1 is 1 over u. But because I switched the limits of integration, I threw in another negative, which negated that negative and gave me a positive. Notice that in this method, I am not going back to x. The 1 and the 5 are actually u values, not x values. Now I do the substitution and subtraction in the order it's now written, always the upper value, whether it's bigger or not, minus the lower value, bigger or not. 1 minus 1/5 would give me 4/5. That's my solution for the area between that curve and the x-axis and between the vertical line x equals 0 and x equal 2. Let's look at method 2 now. If I'm looking at method 2, what do I need to do? In method 2, I start the same. I don't need to change the limits of integration, however. Let's go ahead and write out every step as if we were going to do it without having already done it. I would have, again, that u is x squared plus 1 and du is 2x dx. I can see that I have the 2x dx, which tells me I can now substitute. I would have the integral, replacing the 2x dx would be du. Replacing x squared plus 1 would be u, and that would be raised to the second power. I now have the differential du, but I'm not going to change my limits of integration. I intend to go back to x, so why change? That will let me keep these as x equals 0 and x equal 2. The x equal is no longer optional because these do not match the differential. If you don't write x equal, you're saying that the 0 and 2 are u values, and they're not. Now, once I have it here, I do it the same as I would do it on the left. This means that I would rewrite it x equals 0, x equal 2, u to the negative 2 du. This would again give me u to the negative 1 over negative 1 evaluated between x equals 0 and x equal 2. This time, let's not switch the limits of integration. Let's just leave them. Then I would write the next step, and I would write the negative 1 in the numerator and drop the u to the negative 1 to the denominator. I would also probably then consider possibly in the same step taking out the u and substituting what u is in. In this case, I did it in 2 steps, but it is okay to go ahead and substitute there. U is x squared plus 1. So now I write x squared plus 1 in the denominator in place of u, and notice that I no longer need to write x equals 0 and x equal 2 because I've gone back to the original variable x. It's okay now just to write 0 and 2, since everyone looking at it will assume that they must be x values. Now we will plug in the order that they're written. This will give me the negative 2 plugged in first, or rather the 2 plugged in first, minus, don't forget that the negative 1 is a part of what you got, and thus you have a double negative. Now you plug in 0 from the lower limit of integration. The double negative, of course, will give you a plus, and this will give me 1 over 1, which is 1. The first one will give me a negative 1 over 4 squared plus 1, which is 5. This is negative 1/5 plus 1, which is still 4/5. You can solve these either way. Some students have a clear preference to method 1. Some students have a clear preference to method 2. Again, I will tell you there are occasions where one is easier than the other. You will start to get a feel for it after having done maybe 30 or 40 or 50 problems. And I hate to say it, but that will be about 2 to 3 weeks into Calculus 2 or less. Let's move on. Let's look at our next example, which is example 13. 13 is similar to some of the ones we did earlier. We have 2 polynomial functions inside the integrand. One is the monomial factor 2x, and one is the binomial factor 4 minus x squared. Now, yes, you could just distribute the 2x and then write it as the sum and difference of terms and do them individually. That is certainly one way to do it. However, you can also do this using u substitution. Depending on how complicated the polynomials are, distributing and multiplying out could actually lead to more errors and more mistakes. U substitution is probably the way that we go first if it's possible. In this case, the more complicated factor is the binomial, so that's going to be u. If it's not u, then I might try multiplying out. In method 1, we're going to switch to u and we're never going back to x. That only applies, of course, for definite integrals. For an indefinite integral, you have no choice. You must go back to x, which is probably why I have a slight preference towards that method, since if it's an indefinite integral, you have to go back anyway. I get more practice at that method. If that's u, then the differential du must be negative 2x dx. Remember that the derivative of the constant term 4 is 0, and the power rule pulls the 2 to multiply by the negative 1. Looking at what's here, I have a 2x and a dx, but I don't have a negative. I can simply take care of that, though, without too much trouble, by isolating the 2x dx and solving for it by multiplying both sides by a negative, or you could think of it as dividing by the negative 1 as well. Now I'm going to substitute. However, before I do that, I need to calculate my new limits of integration since I'm never going back to x. Again, I like to write the word when because I only ever do that when I'm replacing limits of integration. And it's a good way to key myself in as to what I was doing and why I did it. When x equals 0, u would be, well, 4 minus 0 squared is 4. When x equals 1, u equals 4 minus 1 squared would give me 3. To replace the lower limit of integration 0, I must put the 4. To replace the upper limit of integration 1, I must put the 3. Notice that this is an example of what I was talking about before. The original limits of integration went from a smaller number to a larger. These are backwards. I'm going from a larger to a smaller. You did not make a mistake. This is the way it has to go. You must leave it this way unless you want to switch them and multiply by a -1. Now I replace the 2x dx with the negative du. I'll put the du at the back and the negative out front the integral. The 4 minus x squared is u, which means that this becomes, just negative the integral of u du. However, I love the negative because if I have a negative on the integral, if I switch the limits of integration, I can get rid of the negative and get a better order on the limits of integration. That would lead to the following. I would get the integral from 3 to 4 of u du, which of course is just u squared over 2 evaluated between 3 and 4. This would give me 16 over 2 minus 9 over 2, which is 7 over 2. That would be my final value for the area between the curve and the x-axis between the vertical lines x equals 0 and x equal 1. Note that the vertical lines are always given in terms of the original variable and the original limits of integration, never the u limits of integration. Now let's try method 2. In method 2, we switch and then we switch back, much like we do for an indefinite integral. It starts the same, with u being 4 minus x squared and du being negative 2x dx. I identify that I have the 2x dx. I isolate that part of the differential du by multiplying both sides by a -1. Then I do my substitution. However, I'm careful to now write x equals 0, x equal 1, since I know that my differential is now going to be du and no longer dx. Inside, I simply get u du. This will then let me write u squared over 2 between x equals 0 and x equal 1. Some students, when they get really good at this, will skip a step between here and here. Instead of writing the u here, from here they go directly and substitute this inside of the antiderivative. In other words, they would go directly to this step and they would write 4 minus x squared over 2 between 0 and 1. I will admit that when I do it by myself, for myself, that is probably what I would do. But then again, I've been doing this for decades, so I don't necessarily recommend it until you're partway through Calculus 2. It won't take you long. You're going to have a lot of practice at u substitution. Once you're here, you will need to plug in the limits of integration. Notice that you have a completely different thing in which you're plugging in the limits of integration from what you had when you did it in the u form. That's okay. That's to be expected. This will give me 4 minus 1 squared, quantity squared, over 2 minus 4 minus 0 squared, quantity squared, over 2. When I do the arithmetic and simplify, I get 1 squared is 1 and 4 minus 1 is 3. This gives me 3 squared over 2. Oops, I've lost something. Let's see where it went. I'm wondering if you now know how I knew I had an error. Being able to find your errors is as important and sometimes more important than knowing how to solve it. I saw that this term was positive and I know it should be negative. I knew then that I had a negative error somewhere. and I track back up, and yep, there it is right there. I forgot about that negative that should have been multiplied by the du. Let's go back and add it in on each step. It's not going to change anything if I think of it as a -1 multiplied on the outside of everything. That then will allow me to finish it without rewriting it, and then I can change the sign. To continue, this would give me 0 squared, which is 0, and then 4 minus 0 is 4, 4 squared is 16, and this would give me 16 over 2. Again, this is 4 squared over 2. This is a negative 9 halves minus 16 halves, which of course is a negative 7 halves. And a negative 7 halves is, you've got it, 7 halves, same answer I got the first time. I will admit that method 2 looks like more work, and I suppose in a way it is a bit more work in most cases. However, it is the standard way of doing an indefinite integral. So in that sense, I think students become more comfortable with this switching to u and switching back. And so they don't find it too much more difficult than switching completely to u. I'll leave it up to you. Use the one you think is best in that situation. We're going to stop here, and I'll leave the rest of the examples to do in the second video over section 5.5, U substitution, undoing the chain rule for derivatives. In that second video, we're going to look at trickier U substitution problems, including some where the choice of U is not obvious, or some where the choice of U is clear, but there are parts of the integrand that don't seem to be able to be replaced easily. We'll take a look at those in the next video.